All right, people, this is the last Zoom recording for this chapter. This is section 3.10, and we will not be covering 3.11, so you're not responsible for that. Anyways, this is about finding the linearization to a given function, any given function. It can also be used for approximations, and I'm going to do an example of that. It also talks about differentials. So the linearization formula, which gives you, by the way, something we've done already, the equation of a tangent line to a curve at a given value of x equals a, is this. L of x is equal to f of a plus f prime of a times the quantity x minus a. So let's run through an example of this. Now, again, this is something that you've already been doing, but not using this, because this is just going to make it a little bit easier for you to find the equation of a tangent line to a curve. So let's say we have the function f of x is equal to the square root of x, which I'm going to write as x to the 1/2 power, because we're going to have to differentiate this. So we want to make sure that we have this in exponential form. So square root of x, pretty basic radical function, okay? So let's take the derivative of this. So therefore, f prime of x is equal to 1/2 x to the negative 1/2. Now, for this example, I'm going to put this back into radical form because we need it in that form. So this is 1/2 times the square root of x. And we're going to find the linearization at, let's say, a equals 4. And I'm choosing a equals 4 because it's a perfect square, and we're going to end up with some nice numbers from this. Okay. So there's my derivative, which I'm going to need in order to find this linearization. And I'm choosing the value a equals 4 because it's a perfect square. So when I plug in a equals 4 into this formula, I get L of x is equal to L of x is equal to f of a at a equals 4 is the square root of 4, because the function is the square root of x, plus f prime of a, which is 4. So that's going to be 1/2 times the square root of 4 times x minus a, which is x minus 4. Now, again, this is in its raw form. I got to do quite a bit of simplifying here. All right. But that's what it looks like so far. All right. So let me simplify this and put it into the slope intercept form, which, by the way, is what all your linear equations for the most part should be. So L of x, the linearization at a equals 4 for f of x equals the square root of x, is equal to 2 plus 1/4 times x minus 4. And that's equal to 2 plus 1/4 x minus 1, which means that L of x is going to be equal to 1/4 x plus 1. Now, one of the things that we can do, and to show you this, is to actually show you on a calculator that this actually works. Now, the calculator is not going to find you the equation of the tangent line, but it can definitely confirm whether you've done this correct or wrong. And that helps. So what I'm going to do with my calculator here, I'm going to go to my y equals window. And first I'm going to plug in my function square root of x, which is the one that I'm using. Okay. And at the same time, I'm going to put in this function. That's 1/4 x plus 1. All right. All right. So I'm going to adjust my window and take a look at what this looks like. So let me try -2 to 10. And let me try -1 to 5. That should be good enough. Yeah. Okay, so there's my graph of the equation square root of x, and there's my graph of the tangent line that I just found, 1/4 x plus 1. Now, we can't tell by looking at the picture of this whether it's tangent, but I can calculate the value of the function at a equals 4, which is x equals 4. So I'm going to go second calc value at 4. And we can see that for both the line and the square root of x, that it passes through that same point. So it is in fact tangent there. Okay, so this is the linearization of the function f of x equals the square root of x at the point a equals 4. Now let's use this, now that we have that equation there, by the way, let's use this to approximate, let's say, the square root of 6. All right. Now, because the tangent line is close to the curve, we can use it to approximate the value of the square root of 6. So I'm going to approximate the value of the square root of 6. Now, once again, I'm going to lean on my calculator. Now, the square root of 6 is approximately equal to, so I'm going to go second calc value at 6. So I see 2.4495. 2.4495. All right. This is, if you punched in the square root of x into your calculator, that's what it would tell you, what the square root of 6 was. Okay, approximately. Now I'm going to scroll up to the tangent line because the tangent line is going to be very close at that point. And the tangent line is telling me that L of 6, the linearization, using the linear function, L of 6 is equal to 2.5. So this means that I'm within about 56 1/100ths of the actual value, okay? So this is how a tangent line can be used to approximate the value of a curve. Now you might want to say, well, why the hell would we want to do that? And that's because when tables are built for irrational values, like the square root of 6 or the square root of 5, they use numerical methods, and some of them are calculus methods, for actually coming up with those values. Now, there is one other topic in this section that you should look at, and that is your differentials. So let me pause this for a second. Okay, back. So the other topic in here that you're responsible for is for calculating either dy or delta y. So let me show you these two formulas. And really, they're just plug and chug formulas. Now, if you really want to understand what they mean, in other words, what is the difference between dy and delta y for different functions, the textbook has some really nice graphs and drawings of that. So if you really want to figure out and understand what they mean, I would look at the textbook or go to a YouTube video and take a look at it. So for dy, you would be asked to calculate dy if you're given f prime of x and the value of dx. Of course, you have to choose the value of x for this, okay? Just so you know. Same thing for delta y. You would have to be given a value of x, a constant, and you would have to be given a value of delta x. Now, dx and delta x measure along the x-axis, and they are the same, no matter what you're using. So let's say that we have, and I'll choose a simple function here. I'll choose, again, let's choose f of x equals x squared. That means that f prime of x is equal to 2x. Okay. And I'm going to, ahead of time here, choose a value of delta x, which is always equal to dx because they're always the same. And I'm going to pick 0.4. Okay, so let me show you this. All right. And then it's really just a plug and chug from there. So that means, and I'm not going to, I won't actually calculate these because you can do these on your own. Just grab your calculator, but I'm going to write this plugged in here. dy is equal to f prime of let's pick x equals 2. We'll make it easy. So it's f prime of 2, which is 4, times 0.4, which is what I've chosen for dx. And that's going to be equal to 1.6. Okay, let me show you this. So I've chosen x equals 2. which means that f prime of 2 is equal to 4. And I've chosen my dx and my delta x to be 0.4. So I'm getting a value of dy equaling 1.6, okay? Now let me calculate delta y. Of course, it's going to be a different value. So my delta y is equal to f of 2 plus f of 2.4 minus f of 2. And I'm just going to use my calculator to come up with this, okay? All right, give me a second, guys. X squared. All right, so this is obviously y equals x squared, all right? Y equals x squared. So I'm just going to use my calculator to come up with the value of this one. So I'm going to calculate 2.4. That gives me 5.76. 5.76. Minus f of x, which is 2. So this gives me a value of 3.76. Okay. So the difference between dy and delta y, you can see dy is 1.6 and delta y is 3.76. Now, this is just one simple example. I would suggest that you pull up some YouTube videos. There should be some listed on the chapter review documents that you should be able to watch. These videos, they're part of the course, by the way. So you should know that you need to be watching these anyway. They are required right along with the course. All right, so this wraps up the chapter, folks. Okay, we're not doing 3.11.